So similar to this convolution between an Eisenstein series and a holomorphic cusp form of weight k, we're going to look at a specific holomorphic cusp form of weight k, a specific holomorphic modular form, but it's not going to be a cusp form, and we're going to see what happens. So recall that this Eisenstein series, the holomorphic Eisenstein series, ek of z, has the following Fourier expansion as constant term 1, and then 2k over the kth Bernoulli number, sum n from 1 to infinity, sum of divisor's function k minus 1 n e to the 2 pi I nz. And this is going to be when k is a positive even integer. So k is 2, 4, 6, dot, dot, dot. Right? Any of these are acceptable. And this is a level 1 weight k holomorphic modular form. And proceeding similarly to what we did for the convolution between an Eisenstein series and a cusp form, let's consider the inner product pi to the minus w, gamma of w, zeta of 2w, e zw. So here this e is the level 1 Eisenstein series. And when I say the Eisenstein series here, I mean the weight 0 Eisenstein series, the real analytic Eisenstein series. And then we'll continue as before, and then we'll put in our holomorphic Eisenstein series here. And take the complex conjugate, like we saw last time. And we'll take this inner product with, again, the Poincaré series at S bar. And things go pretty much the same way as before. So you can just refer to the cusp form. The cusp form videos for how a lot of these go. So what you end up getting is that this inner product here, when you do it just by unfolding as is, not using spectral decomposition, you find that, I find that this is equal to 2 square root pi over 4 pi to the s plus k minus 1 over 2 times, and now here there's this small difference where you have to keep track of this constant term here. So the constant term gives you this L to the 1/2 minus W sigma 2W minus 1 of L over L to the S plus K minus 1 over 2. And then the rest is really exactly the same as before if you just plug in these Fourier coefficients for your ANs, right? If you take AN to be 2k sigma k minus 1n over bk, then you get exactly the same thing as before, but I will write it out. this is 2k over bk n plus L to the 1/2 minus W sigma 2W minus 1 of n plus L, sorry, times sigma k minus 1 of n. So this is going to be coming from the holomorphic Eisenstein series. This is coming from the real analytic Eisenstein series. And then this divided by n plus L to the s plus k minus 1 over 2. So of course you can regroup things if you like. And then it is this quantity times, and you have some gamma functions. The gamma functions are gamma of s plus k minus 1 over 2 plus w minus 1/2 times gamma of s plus k minus 1 over 2 minus w plus 1/2 over gamma of, and I write this s plus k minus 1 over 2 plus 1/2, which, I don't know, maybe it's weird to not combine these, but I think that, it helps me to remember where this comes from, essentially. So this is really basically exactly the same, except you have this bonus term here. And you also have these inner products that you're going to use for the spectral decomposition. So it's just as before, where we found that the inner product of E z lambda with your Poincaré series zs bar was equal to 2 root pi L to the 1/2 minus lambda sigma 2 lambda minus 1 of L over 4 pi L to the s minus 1/2, and then here I'm going to write capital lambda for the completed Riemann zeta function. Then you have these gamma factors, s minus 1/2 plus lambda minus 1/2 gamma s minus 1/2 minus lambda plus 1/2, and all this divided by gamma of s. So here I'm saying that lambda of s is defined to be pi to the minus s over 2 gamma of s over 2 zeta of s, just so that the functional equation is s goes to 1 minus s. So this is the same as previously, right? Of course, there's no there's no dependence on the holomorphic Eisenstein series at all in this, so we're just going to need this later, but yeah, it's exactly the same calculation. Similarly, this is the same calculation as before. There's no actual dependence on the holomorphic Eisenstein series, so I'll just write down what you get. This is rho of L, sorry. So it's the same as for the Eisenstein series. For the Eisenstein series, you could write out what the Fourier coefficient was, and here you have gamma of s minus 1/2 plus IRJ times gamma of s minus 1/2 minus IRJ, and all this divided by gamma of s. So this is with the normalization that your Moss form is written sum n not equals 0 to rho j n y to the 1/2 k I rj. So this is going to be, s times, it's going to be 1/2 plus, s is going to be 1/2 plus IRJ, where s times 1 minus s is your eigenvalue. And then you have the usual Whittaker function, 2i ny e of nx. So this is the normalization I'm using, and with this normalization, this is the inner product you get. So the more interesting bits are going to come from inner products that actually use what we're looking at. So I will just copy paste this for speed. So if we had, so with this thing, but the inner product with the Moss form uj, then what we end up finding is that this is equal to minus 4k over the kth Bernoulli number, square root of pi times the completed Riemann zeta function at 2w. So note that this is lambda 2w. And then divided by 4 pi to the w plus k minus 1 over 2. And then we have some gamma functions, gamma of w plus k minus 1 over 2 plus IRJ, gamma of w plus k minus 1 over 2 minus IRJ over gamma of w plus k minus 1 over 2 plus 1/2. And then we have this convolution, but not a shifted convolution, some n from 1 to infinity of, so previously we had this am here, now we're going to have this sigma. Of course, the conjugate the complex conjugate is just the same thing, right? This quantity is real. And then rho j minus n, complex conjugate, divided by n to the w plus k minus 1 over 2. So it's exactly the same as the case for a cusp form. And the reason why this is all the same so far, and the reason we're going to get a difference for the last one, is because this Fourier expansion of the function that we're taking this inner product with, so here I'm going to write it lambda 2w e zw y to the k over 2 e k z complex conjugate. This has this Fourier expansion where we just take the Fourier expansion from each piece. So this is going to be equal to, and now this first part, the Fourier expansion, this is level 1 Eisenstein series, so it's lambda 2w y to the w plus lambda 2 minus 2w y to the 1 minus w, that's the constant term. And then you have sum n not equal 0 to absolute value of n to the 1/2 minus w sigma of 2w minus 1 of n. Here I'm using this convention that sigma of n is equal to sigma of the absolute value of n. And then the usual Whittaker function. So the k-Bessel function at w minus 1/2 of 2 pi n y e to the 2 pi I n x. So that's just coming from this thing. And then we have times y to the k over 2, and then we have the Fourier expansion that we wrote down involving the Bernoulli number this is sum n from 1 to infinity, sigma k minus 1, n. And then here you can write this as e to the minus 2 pi ny e of minus nx. Because when you take the complex conjugate, it turns the e to the 2 pi I nx into an e to the minus 2 pi I nx. So writing it this way and thinking about how this inner product goes, you can see that the only difference between this thing and the cusp form is the presence of this constant term right here. But when you're taking an inner product with the Moss form, the fact that you have this here doesn't matter at all, right? Because you're going to unfold your Eisenstein series, so this part's not going to matter, and you end up getting this integral y from 0 to infinity, x from 0 to 1 of lambda 2w coming from this thing times y to the k over 2, and then this 1 minus blah, blah, blah. And then for the Moss form, you have a sum n not equals 0 of blah, blah, blah. Maybe I should be a little bit more specific with the blah, blah, blah. We have this sum n from 1 to infinity, blah, 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 e of minus nx. And here we have this blah, blah, and again an e of minus nx, I guess, because we're taking a complex conjugate, but it doesn't matter because it's symmetric. And then we have it's going to be what, a y to the w dx dy over y squared. And you can see that if we want this integral in dx to not vanish, then we're going to need m to be minus n. And m can't be 0. So this ends up not contributing in any way. Okay, so that's why you get essentially exactly the same thing as you did before for this inner product with the Moss form. But now the last thing that we need to check is this inner product of the function that we care about. With this Eisenstein series. So, just Z lambda. And for this one, we're going to run into some trouble. So this won't converge is going to be the trouble. So let's write out what we would normally get, just blindly unfolding. So here, if we think about doing exactly the same thing, and here I'm going to unfold this second term, e z lambda bar, then we get this integral 0 to infinity, and okay, once we sort of pick off the terms that are not going to vanish when we integrate from 0 to 1, we end up with the following. We end up first with this term coming from the 1 right here, right? Because we have a 1 here, and then there's also going to be this constant term in the real analytic Eisenstein series. So these two things, when you multiply them together, you end up getting a term that you can integrate from 0 to 1, and you get something. So you end up with an e, end up with lambda 2w y to the w plus lambda 2 minus 2w y to the 1 minus w, constant term of the real analytic Eisenstein series, times y to the lambda minus 1/2 plus k minus 1 over 2 dy over y. And then for the second piece, the piece coming from the sort of non-constant terms, you get exactly the same thing as before. So for these, you end up with, well, basically exactly what we wrote above, right? We end up with with this, except that the rho j that we have here is going to be this Fourier coefficient of the Eisenstein series. So I think you end up with just a n to the 1/2 minus w sigma 2w minus 1 n here, and then this w here should be a lambda. And these w's should also be lambdas. And probably this w should be a lambda, right? And so this is just coming from looking at this Fourier expansion and saying, what are the rho j's, right? Because we wrote the Moss form this way, so 2 rho j is this thing. So here the rho j is just absolute value of n to the 1/2 minus w. It's this thing, right? So that's just taking it and replacing it with this, and replacing the w with lambda. And when I did this, I didn't get a lambda of 2w here, but I don't know where that went. So I don't know, maybe there's a lambda 2w here, maybe there isn't. Oh, maybe it's because I unfolded the other thing. Anyway, I'm not sure if maybe I'm missing a factor of lambda 2w here, but I guess not, right? Because in the other case I unfolded the other Eisenstein series, so this is gonna be right, yeah. So you end up with this thing, and this second thing, okay, it's fine, but this first thing, this doesn't converge. So why doesn't it converge? Well, I mean, what power of y, we basically just have this integral from 0 to infinity of y to the something, dy over y, and this is always going to be infinity, right? Because either you diverge at 0 or you diverge at infinity. So you, or both if theta is 0, right? So you really you can't win with this, right? This is never, ever, ever going to converge. So this is a problem, right? How do we make sense of this? And the problem is that the function that we're looking at, lambda 2w e zwy k over 2 holomorphic e conjugate, this is not a square integrable function on, and here it's going to be level 1 trivial characters. So I'll just write SL to Z quotienting the upper half plane. And spectral decomposition only works when you are square integrable. So for elements of, or, you know, if you have a different congruent subgroup, you know, then you have spectral decomposition there too. But the point is you need to be square integrable. And we just weren't square integrable, and this is a problem for specifically this inner product with the Eisenstein series, which diverges. So the fun of this is there is a way around this. So I guess stay tuned, and we'll tackle that next.